right, how's everybody doing? All right, good. That's good to hear because it's, what is today, Tuesday? It's Tuesday at reInvent.
Welcome to...
Yeah, that's right. It's Tuesday. You're not going to hear her over me at all. So I will stop talking when it's her time to talk. So, hey, I'm glad y'all are here. My name is Eric Johnson. I'm a principal developer advocate at AWS. And I have the honor and the privilege to talk with this lady here.
Wow.
Please tell them who you are. This is Uma. I already jumped it. Uma, tell them who you are, what you do.
Hi, everyone. My name is Uma Ramadas. I'm a specialist solutions architect on serverless. I am really, really excited to be sharing the stage with one and only Eric Johnson, and very humbled to be presenting in front of you.
Yeah, we really appreciate that y'all have chosen our session, and we're excited. Today we're talking about building event-driven architectures using Amazon ECS with AWS Fargate. Whew, that's a mouthful, right? That's a lot to say. But hopefully you'll learn something. Now, how many of y'all have heard me speak? Okay, so just a heads up, it's the same jokes. So if you want to leave now, I understand. But not enough of you have heard me speak that I have to do the rules, okay? So there are some, did you know there's rules when I talk?
Yes.
Okay, all right, just so you know. So when I talk, these are the rules. They're not hard, but they're going to help you out, okay? The first is, this is any number I want it to be, okay? I'm going to say this. I may say I have 5 kids. Or I may say, hey, I want a table for 10. And I myself alone at the bar, right? So this is any number I want it to be. It'll make it a lot easier. Someone will come in late. I'll hold this up and say 93. And they'll say, that's not a 93. So, which you're right, but it is today. All right, the second is, these are quotes, not apostrophes. And I know that, okay? Because this looks better than this, okay? People think I'm doing a bunny when I do this. Okay, I'm not doing a bunny unless I am. It's contextual. And finally, these are thumbs, because this will get you beat up. Okay, so those are the rules. Hopefully that helps. Abide by them, don't abide by them, I'll be okay. Here's the truth, I make a lot of one-finger jokes. I'm very comfortable being this way. However, and let's take a serious moment, if that offends you or makes you uncomfortable, I'm also comfortable with that. So I'm good either way, and we're gonna have a good time. You good?
Yeah.
All right, so let's get started. So today, we're going to be talking about, and you may be asking, really honestly, here's 2 serverless folks. You're like, what are they doing talking about containers? Well, ECS on Fargate is a serverless container, right? And this, I'm going to be really honest, they're kind of new to me. I'm a serverless diehard. The only compute that ever has lived in the world is a Lambda function, right? Apparently not, but that's been my world. But then I've been opened up to this ECS world, and man, I'm having a good time, and it's very powerful. And we're going to be talking again today about event-driven architectures with containers. All right, so let's get through our agenda. We can talk about, here's what we're going to be talking about. First of all, we're going to talk about what is event-driven architecture, right? What am I saying with that? Some integration patterns in event-driven architecture. What is AWS Fargate? Why is that important? EDA patterns for AWS Fargate, and then we're going to do some wrap-up. All right, so let's get started. All right, so event-driven architecture. Now, we say event-driven architecture, and you really got to start with, okay, what is an event? Because it's kind of like the hero of the phrase, event-driven architecture, right? So what is an event? Now, you may have in your head, okay, an event is like, reInvent, right? It has the word, reInvent, or the party that's happening tonight. But an event in this case is this. It's a JSON object. It's something that has happened, right? So an event is a signal that a system state has changed. This thing happened. They occurred in the past. It's not this thing will happen, or this thing is currently happening. It's this thing happened, right? So events cannot be changed. We can't go back and go, no, that didn't happen, okay? Sometimes we have to modify them by doing another event, something like that, like logging, but events don't change. And finally, events are a contract between the producer and the consumer. And if you think about this, has anybody in here used an API before? Okay, yeah, hopefully, come on, more of you have used, yeah. APIs, they're a standard part of our development life, right? We talk about it to our siblings and our partners and things like that, and they don't care. But we talk about APIs, right? I do, my wife's like, I really don't care. So APIs it's the same idea with events. With an API, when you're sending an API request, You have a contract. They're expecting a certain format to that call. It's the same with event-driven architectures, right? This is the contract between the producer and the consumer. All right, so this is probably the most technical part of this talk, all right? So if you want to write this down, that's fine. But I'm going to define event-driven architecture, all right? And a lot of people miss it the first time. If we have to do it again, I will. But it goes like this. Something happens, and we react. Okay, I went too fast. We'll back up. Okay? Okay, are you with me? Here we go again. Something happens, boom, and we react. Now that's an oversimplification, right? You're like, come on, Eric. They pay me a lot of money to speak. Not a lot of money, let's not get carried away. They pay me money to speak here, let's get serious, right? This is obviously simplified. But this is the idea of event-driven architecture. Something happens, and we react rather than finally, polling to see if it happened or someone having to notify everybody. In fact, let's take a look at this in kind of an example. In a non-EDA world, when we have a producer and it needs to tell the consumers that something's happening, it'll say, okay, this thing happened. Hey, consumer A, this thing happened. Hey, consumer B, this thing happened. Hey, consumer C, this thing happened. The consumer or the producer needs to be aware of the consumers, right? There's this coupling that goes on, and it's a tight coupling, right? And so when you do this in EDA, this looks different. Instead, the producer kicks out an event, right? I designed that event, very proud of it. We were talking about going with the square, but I said, no, Uma, let's go with the circle. I really think that's it. So that's an event, right? And notice there's this big green line between the producer and the consumers that says, hey, I don't have to know about you. I don't want to make you sensitive, but I don't care about you. My job is to kick out this event. Whether you get it or not my problem. I love that freedom that comes with event-driven architecture, right? So when we do this, that allows us to decouple these applications. All right, so we're going to get into some integration patterns and how do we get from this idea of coupled to decoupled and where do we go? All right, so in this, we have this pattern. We've all seen it. If you're a developer, let me ask this question. Raise your hand if you're a developer. I know that wasn't a question. I'm not good with grammar. So, all right, good. So most of the room is developers, all right? Raise your hand if you're using ECS now. Oh, okay, good amount of room. Okay, good, that's good to know. Okay, so when we look at these patterns, this is a pattern we see all the time. This is a standard API pattern. This is the synchronous request and response model, right? We make a request, we wait for the response. If the response fails, the request fails, right? So there's this tight coupling that goes on. Now, some advantages of this, again, are the low latency, the simple, and the fail fast. And I'm going to back up for a minute because I want to talk about that for a moment. The idea of fail fast is actually really cool. They were getting ready to take a picture and I took it away. I'll bring it back, okay? Don't you worry. All right. So the advantage of this fail fast idea says, I want to know right now locally in my development environment if this doesn't work. So this is really handy, and that's an advantage of synchronous. But there's some disadvantages. There it is. Go. All right. Okay, all right. So disadvantages are you can run into throttling, right? So the producer has to talk to all these people, right? And if one fails, they all fail. It becomes problematic, right? It adds complexity. All this logic has to happen inside the producer to talk to these consumers, and you run into resiliency issues, which we just talked about, right? So we want to talk about moving from asynchronous to synchronous communication. And the way we do that is we introduce something in the middle. And we'll call it a broker, right? And there's different terms we'll use for this. But the broker, their job is I send the request, and all it does is acknowledge. It just says, hey, I got it, thanks. I didn't do the work. I'm not doing the business logic. I'm not the process on that. I'm just saying, hey, I got it. And then through either a push or pull process, then it's going to get that data to a consumer. And the consumer may not know where this came from. It doesn't care. It just knows, hey, I've got data, and now I need to do something. I have an event. This is event-driven architecture. All right? So there's several ways we do this. Okay, first one we're going to talk about is event routers. There's that circle again. Pretty proud of that. This time it's pink to shake things up. All right, so event routers, right? They route one event at a time. I can do one, okay? They route one event at a time. They target multiple endpoints and protocols usually. You filter at the router is generally how that works. And then on AWS, when we build in these routers, we usually build them to have configurable retry and configurable DLQ. So the first pattern that we're going to look at this in an event router is the event bus. The event bus is really cool. So it's going to reduce location coupling. It's really efficient for the sender. And here's where it gets really cool. It handles the logic for routing at the rule. Not at the producer, not at the consumer, but at the rule, right? So you can see here in this event bus, it has the rule for doing that. And the service we do this with is called Amazon EventBridge. Anybody using EventBridge now? All right. So if you're a developer and you have an AWS account, you should raise your hand because actually everybody has a default bus. You may not be using it, but it's there. You're welcome. All right. Okay. All right. So let's look at how EventBridge works. You have one in your account. All right. I like to see if you're listening over there. Okay. All right. So here's how EventBridge works. First of all, you have these sources, right? It can be AWS service, custom applications. You can be building a custom application, all kinds of things. They're the sources, right? And they're actually going to send data into one of your buses. And this goes back to you have a default bus, just like we talked about, right? And so they'll be kicking in that. And already, EventBridge is, CloudWatch may be sending into that. The system's talking through the default bus. It can be a custom event bus that you create. It can be a partner bus, all kinds of different things. But here's where the power of EventBridge comes in, all right? This is where we create the rules. And I love rules. Remember, I have rules? Okay. So rules are good, right? And I'm a dad of 5. Rules are good. All right. So the rules allow you to say, I'm going to match, if you match the rule here, I'm going to send the data on to a target. Right? So let me show you this in kind of an idea. So we have this event, right? And in this event, it's a pizza ordering event, right? And you'll notice it's a proper event because it says no pineapple on pizza in the name, right? So that's really critical and important, probably the most important thing I'm going to say all day, right? Because there should be no pineapple on pizza, and you can see that, right? And this is all about real pizza, proper pizza, and so on. So this is what our event looks like. Got that? Yeah. All right. Okay, so this is what our rule looks like. And the rule is very simple. You basically say, okay, I'm going to say the source has to come from com.flex. And notice that's an array. I can match more. There's a lot of power you can do with this. And then the region needs to be from either Australia or New Zealand. Right? And so, sure enough, if you'll notice, com.flex is the source, and the region is one of the matching. So this is a match. It's that simple. And it really is kind of funny. I joke and play a lot, but it's amazingly simple, but amazingly powerful, right? All right, so then what happens is then we have these rules that are going, and then they hit the target. And the target can be, you can see here AWS Lambda, Amazon ECS, which we're talking about today. We'll jump into that some more. API, there's all kinds of places you can point this at. So that's the event bus part of event routing. So let's look at event routers with topics. Now topics, the idea here is instead of, they broadcast to multiple consumers and you filter the consumer at the topic. You have some filtering ability as well. Every consumer gets the same topic unless you're filtering it out there, right? It's consumer A, B, and C. Excuse me. Now, they support multiple protocols. So this is really cool, at least the topics that we use, which I'm going to talk about here in a moment, is SNS. I can actually send to email. I can send to SMS. I can send to Lambda. I can send to an external API endpoint. There's a lot of things I can do this. So this is a very powerful tool for fanning out information. So basically you say, this is the topic. If you want to know something about it, subscribe to this topic. When I send data, you'll get it. All right? So the service we use for this is Amazon SNS. And I'm gonna read this. I love this standard topic support, and this is in the documents, okay? So we like to do hard, fast data. Support nearly unlimited number of messages per second, right? It is a very powerful system that handles tons of data, right? You can have up to 12.5 million subscriptions. You can have FIFO, which means first in, first out. Super powerful service, and we use this for messaging. All right, so that's kind of the event routers. So the next pattern we see is called event stores. And event stores will handle multiple events, right? So we're no longer doing one at a time, we're doing this array or batch of events, right? So how this is gonna work is data is gonna come in, you have these messages coming in, and then consumers will consume it. Now, notice the top one is getting message 6, 5, and 4, the bottom one's getting 3, 2, and 1. Not all consumers get all messages. Actually, only one consumer should, right? And they process this at a time, so this is a little different. So this is really handy for, hey, we have to process a lot of data, so I need a farm of consumers, but I don't need duplicates. So I'm gonna fight against duplicates by building an idempotent system that only one consumer will process these. It also supports a DLQ here, as you can see. Order can be enforced, like I said, using the FIFO, just like we talked about with SNS. Now, multiple consumers needing same events, and this is an interesting call out, so you know this, if multiple consumers need this, then you're gonna need multiple queues, and you're gonna need to fan those out, so you could use a topic, fan out to a queue, and that would, you could use multiple queues for the consumers. All right, the service we use for this, and we have several, but the one that I'm highlighting at the moment is SQS. It's a fully managed message queue. Again, really, really hard number of data here, scales almost infinitely. So really, it scales large and fast, right? Simple, easy to use API, DLQ support. Another service that we use is Amazon MQ, right? And this is ActiveMQ and RabbitMQ. Anybody using ActiveMQ or RabbitMQ? Okay, you can do that as a managed service on AWS. Hopefully, maybe you're doing it that way. If you like that open source, that's great. We have a way for you to manage that. We'll handle the operations of it. You handle what makes you money, right? All right. So the next pattern we have is the event store stream, right? So this is a little different, right? This is data coming in. All services will get what's coming out of it, so that it goes to each of the consumers, right? All consumers get all events. Filtering must be done at the consumer, right? So you can't filter at the actual broker. Your consumer has to get that data and go, do I want this? Yes. Do I want this? No, right? So that's important to understand as you're trying to pick which one you're using, right? Orders enforced based on different parameters. So this is going to enforce order out of the box, and you can change the parameters on that. Services we have for that are Amazon Kinesis data streams, which has gigabit per second streaming. This is a very, very fast scaling system that can take much data. It's built-in integration with other AWS services. We also have Amazon MSK, which is fully managed Apache Kafka. Is it Kafka or Kafka?
I say Kafka.
Okay, Kafka. We're gonna go, Uma's so much smarter than I am, so we're gonna go Kafka, all right? And she has the cool accent. I can't say it with the cool accent, so. All right, so there's managed Kafka. So if you're using Kafka out there, the managed Kafka is actually, it's a really cool service. We're doing a lot of work around that. Okay, so I just threw a lot of data at you and a lot of information on some of the different patterns. So let's kind of get into the meat of this when we're talking about what is AWS Fargate, because that's kind of where we're headed today. And for this, I'm going to pass it over to Uma.
Thank
Got
you.
it. Go, Uma.
All right. So all of the services Eric talked about, they're really crucial for integration. The wiring that connects your distributed components and microservices. You can use containers to build, package, and deploy your microservices. What is the best way to run your containers without worrying about the underlying instance? That's where AWS Fargate comes into. Fargate is a serverless compute engine that lets you use containers as a core compute unit without you having to manage the underlying instance. All you have to do is to build, package your code, and specify a few requirements such as CPU, memory, network settings, and you're good to go. AWS makes sure your container is run in isolation. It's patched and compliant. Plus, you get the per second billing granularity. And so sometimes you want to run your application as a one-off application that you want to schedule or you want to run on an event. So the way that you would run is run as a standalone task. When you run as a standalone task, you're just running it when you need it. What you would do is to specify, again, CPU, memory requirements, and you invoke the run task API. ECS makes sure it runs a task. It just provisions the task, runs your code, and then it just gets rid of it. This is a really cost-efficient approach to run your one-off task because you're only running it when you need it. There are a lot of times you want to run your application 24/7. Like, for example, you are hosting a website, or you're running a backend API, or you're processing messages from a stream. So the best way to run it is to run as a service. When you run as a service, you are running your application all the time. When you do that, you also want to run a fewer copies of your application because you want to meet the traffic demand as well. So just like before, you specify CPU, memory requirement, package your code as container, and then you specify how many copies you want to run. ECS constantly makes sure it maintains our desired copies. The tasks here are actually self-healing as well because when a task dies, ECS brings back a new task to replace it. So as you can see, Fargate allows you to focus on business value. But what makes Fargate suitable for event-driven architecture? When you run or your architecture is event-driven, you observe certain inherent qualities in your architecture. For example, it will be scalable, robust, reliable. It might be embracing microservice architectures. It might be running purpose-built services. So when you choose a compute that allows you to run event-driven application, it should make sure, it should make it easy for you to build with those characteristics in mind. Fargate allows you to build scalable application. It gives you multiple different scaling techniques that you can use to build scalable applications. We'll look into some of the scaling aspects later in the session. Microservices are backbones for event-driven architectures. With Fargate, you can go as small as 0.25 vCPU and 512 megabytes memory, which means you can build single-purpose microservices, package them as containers, and deploy them frequently. That's an enabler for building event-driven architecture. Fargate integrates natively with some event-based services, like Amazon Event Bridge, AWS Step Functions. They all allow you to compose event-driven applications easily. Lastly, you can leverage Spot Compute. When you are processing messages from streams or queues, the messages are actually durably stored, which means even if you are using Spot Compute, you're building loosely coupled architecture and processing messages reliably. So what we have seen here, we have looked at few integration patterns. We looked at why Fargate is for event-driven architectures. Now we're going to see some patterns around standalone tasks, long-running services, push-based pattern, pull-based pattern, etc.
All right. I forgot my clicker here. Here we go. All right, so we're talking about why AWS Fargate is a good match for this, right? And so when we think about, we kind of transition this, when we think about traditional ECS, traditional Amazon ECS on Fargate, this is how it works, right? We have a task, we've got our service, we've got AWS Fargate, it's all running Amazon ECS, and it runs all the time, right? So it's up and it's running whether I need it or not, right? And so sometimes that's idle, and as developers, actually developers don't care. Idle's fine. The people paying care, right? Idle's bad, right? So we don't like idle. So if I run, and if I have constant services, then this is what we need. But what if I don't need it all the time? I just need it sometimes, like when an event happens, because that's event-driven architecture, right? So what if I took out the service and I said, okay, we're going to use Amazon ECS, we're going to use Fargate, but instead of the service on Fargate or ECS running that, we're actually going to run it from Amazon Event Bridge or AWS Step Functions. And I remember we did this, I first learned about this last year, and I thought, oh, this is so cool. So what I can do is actually have the task, be described or built by EventBridge or step functions, and then have it go and do the work. And much like Uma said, it does the work and it goes away. So let's look at some patterns with the standalone tasks and how that works. Now I have some cool animations here, so buckle up. Y'all ready? Okay, so we have, and I can't talk fast enough for these animations, I'm gonna be really honest. So we have, a video comes in and it goes over there, okay. All right, let me tell you what happens right there, okay. So we had a video come in, and this is actually based on a project we built last year. We were processing videos. We were processing videos with serverless. It can be done, right? That's a thing, right? And so we're processing these videos, and when they get dropped in the bucket, then it would kick off an event, and that would go to EventBridge, and then we would actually send that to Fargate, and it would run that one job, and then it would go away. And we could have it continue to run other jobs, come up, do it, go away, right? So this is event-driven, or I like the term, I don't know if I've coined it yet, but I'm working on it. You ready? Buckle up over there. Event-based, that's not mine, somebody else said it, but event-based containers, right? Containers that are running based on events. Okay, we're done, right? So this is a way to do large object processing. You can do that event-based. You can also apply this to scheduled processing. So let's say I have some type of service that I need to run at night. So what I can do is I can say, okay, every night at 9 o'clock, I want you to run this process. I could kick out an event to EventBridge using the scheduler, and then it will actually go and run the Fargate. I'm sorry, I don't have any cool animations on this, but you saw the ones on the last screen, right? So those are cool, yeah. All right, so, and then it runs it and it goes away. This is a really cool way of getting more compute or more time than you might do with other ephemeral like a Lambda. However, there are some considerations for this, right? So, use when AWS Lambda is not a good fit. We built AWS Lambda for a very specific reason. We built it for ephemeral compute that comes up, does its job, and goes away. And it can do it at massive scale, right? Containers were built to do longer running and do those kind of at massive scale as well. So you don't want to slam this API. You don't want to say, okay, bring up 1,000, take down 1,000, bring up 1,000, take down 1,000. That's what Lambda functions are for, right? If you end up doing that, you just run the system, right? You just run a container in a service, which I'm just taking your thunder right now, which Uma's going to talk about, okay? All right, so task failures need to be managed separately. That's another thing, right? So you want to make sure that when something fails, you're handling that, be it via the DLQ, something like that. Again, use the DLQ. Burst can cause scaling issues with tasks, and that's what I was just talking about. When you burst hard against that, because that's not what it's designed for, right? Burst, we designed for radical burst up and down, again, is for Lambda, so you want to know which of these you want to use. All right, so I know I stole a little bit of your thunder, but I'll pass it back over to Uma here.
So we are going to get more technical. We're going to talk about patterns for your applications that are running 24/7. We will start with patterns or push-based patterns where you can use EventBridge to send events to public APIs and private APIs. You did not hear me wrong, private APIs as well. This is a new launch, hot off the press for you. And then we'll talk about processing messages from queues, and we'll explore the pattern. We'll also explore the capabilities. APIs are backbones for building microservices. So if you have asynchronous APIs that just get a request, immediately send a response, that again go behind and do the task. For example, you are creating a task whenever, or creating a ticket whenever a customer complains, or you're sending an auto-created event notification to a shipping service. So if you have an asynchronous API that is publicly available, or any public APIs that you want to call, then you can make use of API destination. API destination is a feature of EventBridge that allows you to send event notification to any public APIs, Zendesk, Stripe, Twilio, or your own public APIs. You can send events from Fargate task instances or any producer that you're running in a compute. When you send the event, you can apply rules and filters. For example, you can check if the channel name is no pineapple on pizza, and it's for the user in Asia. Only if the event matches the filter criteria, the event is sent to the API endpoint. API destination also supports multiple different authorization options. So if your API accepts or expects API key or a basic auth or OAuth authorization, you can easily configure it in the API destination connection. And EventBridge manages securely the credentials in Secrets Manager. Plus, the access to the Secrets Manager API comes free with it. What I really like about API destination is it allows you to put or apply some back pressure when you're invoking the APIs. Any APIs, you should be mindful of the rate at which it can accept the request. You don't want to blast them off with too many events and overwhelm the system. So API destination allows you to put rate control. So when you specify the rate control, EventBridge makes a best effort to send at the rate that you specify. So it will only send at the rate that you want your API to be invoked. Failures are natural. They are bound to happen. So when things fail, EventBridge will retry for up to 24 hours. If still things fail, you can configure a dead letter queue. This is new. This is what I was talking about. From Sunday this week, you can send event notification from EventBridge to your APIs that are inside VPC, perhaps behind load balancers, only available internally to your VPC. This is really huge for building event-driven architectures because you can now build cross-domain, cross-account, cross-system, or between AWS and on-premise event-driven applications. The developer experience of private API destination is kept really simple and consistent with public APIs. So all the features that I talked about, rate control, retries, dead letter queue, and the multiple different authorizations, everything is available with private API as well. So as a consumer of the API, you're really connecting to a private endpoint instead of a public endpoint. The provider of the API is the one who is going to decide or who's going to provide all the access. They're going to specify how the consumers are going to access it. The consumer can be in the same account or across accounts. So they do that by using a new primitive called VPC resource access. And so what we so far looked into is how you can build loosely coupled architectures by sending events from EventBridge. Now we're going to look into some pull-based pattern by processing messages from SQS. In the interest of time, we're going to use SQS, but this pattern, the capabilities are very similar for other types of queues as well. When you use SQS between two services, you're actually controlling the flow of messages from the producer to the consumer. We earlier talked about how EventBridge applies the rate control before sending it to the APIs. Now here, the rate control is determined by the consumer. Your Fargate instance, or the task instances, are the one who is going to control the rate at which it is going to consume. So processing messages from SQS is really straightforward. You write a few lines of code, and then you package your code, deploy it as a task instance. You want to process more, then you add more task instances. Think of a coffee shop example. If you have just one barista serving all your customers, adding more baristas will speed things up. Similarly, when you add more task instances, you're going to process more messages. After you process the messages, you will delete the messages. When you have constant stream of messages coming in, you really don't have to adjust the resources, right? When you have always 2 baristas and 4 customers, you really don't have to add more baristas. But in reality, it is rarely the case. You're going to have more customers in the morning than afternoon. And in the real-world applications, you're going to see unpredictable patterns. If you don't handle that unpredictability, you could get into some issues. Again, the coffee shop example, if you have less customers coming in, you might be overpaying your resources. If you have more customers, 2 baristas may not be enough to handle all the customers. So you're increasing the wait time for your customer, and the customer might leave. And so actually, when you're processing messages from queues, this is very, very similar. And so the way to solve that is to adjust the processing capacity in sync with the flow of messages that's coming in. You can do that by dynamically scaling your task instances using either predefined metrics or custom metrics. The easy one first, predefined metrics. SQS publishes approximate number of messages visible metric. This metric tells you how many messages are in the queue waiting to be processed. You can use that metric, build out a scaling policy in just a few lines of code, and this policy essentially scales out the number of tasks when the queue is really, really active. And it scales back in when the queue empties out. So it's really straightforward to keep the number of task instances with respect to the number of messages waiting in the queue. But there is a problem. It only looks at approximate number of messages visible. It does not look at how long it takes to process the messages, nor the acceptable latency. So again, going back to our coffee shop example, some orders take longer than others. If you're just looking at the number of customers in the queue, if not looking at how long it takes to serve a customer, you might be increasing the wait time for the customer. And so the way to solve that is to use custom metric. And here, the custom metric is backlog per task. It is a combination of 2 metrics. SQS, approximate number of messages visible, and the number of running tasks. Because it is a combination of metric, you need CloudWatch metric math to calculate or to derive this metric. Then you need a target by which you are going to scale up or scale down. And the target is the acceptable latency. So when you have the metric and you have the target, then you can create a target tracking policy to scale up and scale down your resources. There is a fantastic guide about how to go about doing it, but you have to wait till the end to get the link. There is also a feature in ECS. It's called task scaling protection. When you enable it, it makes sure your task instance is not terminated in the middle of processing during the scale down event. All right, we have now looked at building loosely coupled architectures with APIs and also with SQS. Coupling is not always bad. Generally, you want low coupling at the higher level of your application and tight control at the lower level of your application. So we are going to look into how you can build the lower level application with some tight control patterns.
All right, thanks, Uma. Okay, so we're going to dive into, this is really fun, we're going to dive into some of the serverless services and how kind of ECS can work into that. The first one we're going to look at here is step functions. So like Uma said, we've talked about this kind of choreographing events and running those and how do we move them around, but how do we start getting control over when things run? How do we orchestrate that? And step functions is a really strong option for this. This is the pay-per-use, it scales automatically, it's fully managed. This is a workflow service. I did a talk on this yesterday morning if you want to catch YouTube on advanced patterns for this, and it talks a lot about how these work and how these go. So the next other one we have is Amazon Managed Workflow for Apache Airflow. Whew, the internal name for that is Mwaha. So there you go. I don't know if I was supposed to say that, but hey, let's keep that to ourselves. Edit that out if you can. So, right, so this is easy Apache Airflow. If you use the open source for that, that's another way of doing that. I'm mainly going to be talking about step functions, so let's jump into that a little bit. So there's a couple of patterns we can use when we're using step functions to talk to ECS, right? And again, this is back to this idea of just using ECS when we need to, right? Bringing it up, doing the work, that kind of stuff, right? So in this is what's called the async pattern. And this is an asynchronous invocation where we just fire and forget. Hey, we need you to do this. I don't need anything back from you. I want you to do this, and I'm going to move on. And then actually, you could just call this, and it's a run task operation in step functions. You send it the data, and it does the work, and step functions moves on. This works really well. But sometimes, in fact, a lot of the times, when you're doing the stuff with ECS or the compute, you need to wait till it's done, right? So it's important to say, hey, do this work, and then when you're done, I can move on. So the next pattern we're going to look at is what we call the sync pattern. And how this works is it's actually you're going to send the data to, again, ECS using the sync call, and then the system's going to handle this for you. It's going to describe the ECS task, and it's going to wait until the task is done. You don't have to do that work. It's just handling it for you, and when it's done, then you'll either get a success or a fail, and you can react to that and move on. Right, so this isn't a fire forget, this is a fire and wait for it to be complete. But there's one more we have here, and a lot of times we need data back. I mean, that's the reality. We want to crunch, we need the power of this compute, but we need to know what the result was, right? Not just that it was done, we need data back to continue processing this. And this is what we call the callback pattern, right? And the callback pattern uses a token to send task completion. Right? And so what it does is you send this to ECS and you send it with the token, and then step functions will stop and wait. ECS, the task comes up, it does the work, and then the last thing you do, and this has to be in your code, is you call back to step functions with that task token. And a step function service is going to know what workflow is running and what I need to do. And you can have two calls, right? One is success, the other is failure. So you let it know, and then it does its thing, right? And that's pretty much it on the patterns. So.
Right, you conveniently forget it. Another one because you heard it from me.
All right, you go.
Actually, we've got two more because of the launch.
That's right.
Right. When you are invoking the run task API every time an event comes in, it might be okay for low, consistent traffic, right? But what if you're getting events like this? S3 will get you a burst of events. Step functions might be able to handle that scale. And you're invoking the run task API for every event. And you'll quickly overwhelm the run task API limits. So it really is not the right way to do it when you have high traffic, or like consistently high traffic, unpredictable traffic. And you know the answer how to handle that. You can use queues, right? But there is also another way to do that. Step functions activity. Anyone heard about step functions activity by show of hands?
Okay, good. I'm going to interrupt for a second here. Okay, so when I was doing this and I was working through the deck, I was like, okay, where is it? And she literally said, are you going to show the activity pattern? And I said, of course I am. What is it? I think this is a seriously underrated, underknown service, and I know it now. Okay, let's get, I know it now, all right? But this is a super powerful way of interacting with step functions, give you some asynchronous power to handle that. I'm gonna turn it back over to you, but it was good to know that nobody raised their hand. I appreciate you.
So activity is a resource in step functions that allows you to build loosely coupled architecture between your workflow and the consumer. You create the activity in step functions, and once you create it, it is available for you to send and receive messages. And so in our use case, instead of sending the event, instead of invoking the run task API every time on an event, you will be sending that event to the activity. And your task will just go to a pause state until the event or the message is processed from the activity. So when the event goes to the activity, it gets stored in the activity. So in the other end of the activity is where the magic happens. This is where your ECS task instances will be processing messages from activity, very similar to how you process messages from SQS. So when you receive messages or your task instances receive messages, they receive something like this with a task token. And that token maps to exactly which workflow, which state it bended out this message. And so your consumer will process your message, and after it processed, it needs to send back a response, because when you're processing messages from queue, you delete the message, right? So in a similar way, you send a response back to the workflow, along with a token and with additional messages if you have. Then the workflow will return to the next step. It will understand the token, get the response message, takes decision based on that. As you can see, this is basically using a queue with a callback token. So
let me ask you a question. Okay. Can only one step function use the activity?
No, you can. You can send it. The activity is a common resource. You can create multiple activities, but you can use the same activity to send messages from one or more workflows, one or more execution of a workflow. And then on the other side, you're processing messages, like if you increase the task instances, you will process the messages faster, just like processing from queue.
How many of you are going to go try an activity later? Yeah, this is cool. I agree. All right, I'm going to be quiet. I won't interrupt you again until I do.
As you can see, you can implement this pattern using SQS with step functions callback integration. So why would I use activity? Activity, like I said, it is part of step functions. It's not a separate service like SQS. SQS is a separate service. It's a lot more powerful. It's got a lot more control and flexibility as well. The messages in the activity, they can be stored up to a year. So if you have a low scaling consumer, you have a consumer in on-premise, it doesn't scale up at all, and you want to keep the messages stored in the activity for a longer period. SQS has a retention period of 14 days. So let's say you want to keep these messages in the buffer more than 14 days, and because your consumer is low scaling, you would prefer activities. Again, we said activities are managed queues with 1 year retention. We looked at how you can process messages in the containerized environment in AWS. You can also process messages from on-premise environment, from activities. You can build loosely coupled architecture because your consumer can scale at a different rate than the arrival rate of your messages from the workflow. Because the messages are stored, you can also leverage for spot compute. That can save you cost. And our last pattern for today is a new launch. So just like EventBridge, step function can also invoke a private API, the API of your application that perhaps you have behind a load balancer, only visible to VPCs or your on-premise APIs. People who have used public APIs with step functions know that you don't have to have any additional compute. You just provide a few configurations and you can invoke the API. Step functions will wait for the API to complete and then move to the next step. It's a very similar experience. And the public APIs uses EventBridge connection to invoke the API. Connections support multiple different authorizations. So again, private APIs also use EventBridge connection. So when you have this connection, you can share this connection between step functions and EventBridge. And it's just one connection that goes to a private endpoint. This is huge for building microservice orchestration because predominantly we have been building microservice orchestrations with step functions and Lambda. Now you can build microservice orchestrations with your APIs that are inside your containerized environment, that are in on-premise. You can build modern applications that bridges your on-premise with AWS. All right, so now it's time to wrap up because we have looked at building loosely coupled architectures. We have looked into how you can build lower level applications with orchestration patterns. We also looked at synchronous pattern like private API integration. So it's time to wrap up with some final thoughts from Eric on event-driven architecture.
Man, do I have thoughts. We could go hours on the wrap up, but I won't, because we have other places to be. So I love this quote. This guy, I don't know if y'all recognize this guy. This is Werner Vogels. He'll be speaking on Thursday. He has quite a few famous quotes, but one of them is systems that don't evolve will die. The reality of our industry is you need to evolve. And so when you're building event-driven architecture, we didn't invent event-driven architecture. I'd like to take credit for it, but I didn't, right? It's been around for years, right? But it's become very popular lately because there's a lot of the services that AWS and other providers are building allows you to build these distributed microservices as event-driven architectures. So people are kind of clamoring to get into EDA and figure out how it works. And so I want to talk about a little bit real quick on where do you start your EDA journey. Really the truth is it's all about understanding, right? So we have a lot of folks that are like, look, I'm just going to start building. And you're developers. I know who you are. You're like, I will code now and read later when I can't do it, right? That's me too. How many of y'all just code until it works? Right? Okay, yeah. There's one guy in the room, I'm not going to point him out because he doesn't like that. He's actually the creator of CDK. If you've used CDK, and I have watched him code, and he codes while talking to, hey Eric, how's it going? And it works. I hate that guy. But we code until it's broken, and then it works, and then we don't know why it works. Right? Understanding. With EDA, I highly encourage you to learn. Take advantage. We got some resources that we're going to show you in a minute. Learn about EDA and kind of the thought process behind it. There's a guy named David Boyne who is well known in the EDA community who has a lot to say about this. But do build, right? I'm not saying don't touch the keyboard, but plan and learn. It's all about understanding. The more you understand, the more you can build, and it keeps you from building these one-way doors and being able to back out. So I really encourage you to do that. I promised you some resources, and here they are. Take a grab of that. S12D.com /SVS 339. I'll leave that up for a second. I'm going to count on my fingers. Okay, we're done. I can get to 4 with my shoes off. All right, so check out these other sessions that are going on. They're all Wednesday, Tuesday. We might have missed one, but that's all right. They're being recorded. I encourage you to check these out. Talk about the same topic. Continue your serverless learning. I really encourage you, the S12D.com serverless learning. And with that, I'm going to say thank you very much. Uma, I want to tell you.
Thank you so much.
Hang on. I appreciate you letting me talk with you. This was fun. Thank you very much. So.
Thank
Uma's the
you
bomb.
so much.
I don't know if that's still cool. Go ahead. Yeah.
Thank you.
Sorry, I talked right over you. So, thank you very much.